Our first speaker is going to be Herman Espinosa. He is going to talk about leveraging spatial connectivity for more efficient planning in naturalistic scenarios. He's currently a CS PhD candidate at Northwestern University working with Malcolm McIver. And without further ado, I'll just let him present.
Hello, everyone. Thanks for being here. Sorry about the little mishap, and thank you for the introduction. All right, so I'm Herman, and I work with Malcolm McIver at the Center for Robotics and Biosystems at Northwestern University. Our main research focus is in planning, and I want to start with a big disclaimer because I know we have a few neuroscientists here. We don't know how planning is done in nature, and we don't know if biology solved this in a complete different way, but we have a very strong we have a very well supported hypothesis that claims that the brain uses the information available and its knowledge about the environment to create a prediction, to create a tree of predictions, and then uses those predictions to select actions that will eventually maximize the probabilities of achieving a goal. We will assume this is true for this talk, even though we know it's controversial still. We will assume it's true for this talk. Then the next question is how big this tree of prediction has to be able to effectively plan, and what it should cover. And in this talk, what I will show you is how the volatility of the environment and the uncertainty about the present increases the number of predictions necessary to effective planning. And I will also introduce you an approach that is theoretically possible in biology to drastically reduce the number of predictions while still maintaining similar outcomes. One of the aspects that increases the complexity of planning is the volatility of the environment. In a static environment, it's easy to create the right predictions, right? Because nothing changes. And those predictions can help us create a perfect plan. And then we can just follow it to conclusions because the environment it will be the same. But if in a changing environment, making predictions is a lot harder, and we must explore all possible values of every single possible variable that we cannot predict. And this grows exponentially with the numbers of actions into the future. So that means if I don't know if something is going to happen or not, I need to plan for both the scenarios. In other words, the less certainly we can predict the future, the bigger our prediction tree is going to be. But what happens if we're not even certain about the present, right? Well, let me explain what I mean with this. Let's say in a naturalistic environment, during a predator-prey interaction, the prey goes behind an occlusion and temporarily loses sight of the predator. Using just the current information, the prey could assume the predator is no longer present, or it stays static on the last known location. We know both assumptions are really detrimental to its chances of survival. But something better the prey could do is use its knowledge about the environment and the predator and guess possible current locations with some level of certainty. We call these guesses a belief state. And in this case, we can see it as a list of possible locations of the predator and the associated probabilities. Once built, the belief state can be used to create multiple trees of predictions and then combine them in one big tree to determine the best possible plan. However, this means the more sparse the belief state is in the space, the more predictions the prey will have to explore. In other words, the less certain we are about the present, the bigger our prediction is going to be. As we've seen so far, our knowledge about the present and our ability to accurately determine the future impact the number of predictions necessary to plan. And I'm going to give you a practical example with a simulated experiment we did just to show you how this works. In a square grid, we located a prey and a predator agent. And sorry, 1 second. There you go. We provided the prey with planning abilities, and we rewarded only when it makes it to the goal in 50 steps or less. The predator has two behaviors, search and chase, and it's averaged 50% faster than the prey. Something important is that both behaviors are stochastic, so the prey cannot predict those deterministically. And finally, we added occlusions that limit the movement of the agents and also their visual fields. So they can only see each other and know where the other agent is when there's an open straight line between them. This introduced the concept of partial observability, and it forces the prey to create a belief state. For this very simple scenario, right? If we want the prey to visit every single possible prediction in the tree, it will have to visit over 10 to the 30 branches. So the only realistic option is to limit the number of predictions it's going to sample from and make a decision based on the information it can get from that. We needed to set that number for this prey, but we didn't know how much the prey needs to sample to be able to make a good decision. So we created an experiment. We incrementally increased the number of predictions we let the prey sample from until we see that the survival rate maxed out or a plateau. We started with 100K, which is a big number in computing power. And the behaviors we saw were very close to random. And the survival rate was very bad, very poor percent. And one of the things that we observed there is like it did not get better for many increments. Only got to a 8%, 8.4% survival rate after 100 million iterations, sorry, 100 million predictions. And we can only see from this graph, there's a little bit of improvement happening after 50 million predictions. So this is kind of like a strange situation because it looks like it's a super complex problem for a simulated prey, but we know that biology could deal with this with an incredible speed and with simplicity. Another interesting discovery from this experiment was when we explored the predictions that the prey was exploring while making a decision, most of the time it was spent exploring branches of the tree that had no opportunity whatsoever. So basically it was looping back and forward in open space in front of the predator, for example. Here's the second part of the talk, and I told you I was going to give you a biologically possible method to drive down the number of predictions and maintain results. But to illustrate to better on how we got there, I have a quick game. Let's please play with me. You have to imagine you're a 12-year-old kid again, and it's very important that you put yourself in that role. You're a 12-year-old kid, otherwise it won't work. Now imagine that it's Halloween and you're trick-or-treating around the neighborhood, and at some point you make the wrong turn and end up at the gates of an abandoned factory, exactly like in a horror movie. You hear a noise, you turn around, and there is a big monster running towards you. You run to the factory and open the door, and this is what you see. Now, I only gave you 1 second to look at that picture, but if I ask you what features do you remember from that image, there will be many different answers, but two will remain very consistent across all of them. Two features will remain very consistent across all of them: the broken window and the columns. And it makes sense because these two features contain opportunities to exploit two behaviors we know are very useful while escaping from a predator: fleeing and hiding. So it makes sense that we're equipped to identify these features very quickly. But the question is how? Well, previous research in our lab found evidence that suggests that early mammals might have evolved a sense of connectedness of the space based on visual cues. This was very useful, you can imagine, as animals on land can see much farther than animals on water. Hence, prey need to know if the space was occluded enough not to be seen from far by predators. Let's see how the connectedness of the factory we just saw looks like. This is a 2D representation of the factory. You can see the columns and the window. And we use eigencentrality to determine the connectedness of the space in the map. Eigencentrality doesn't only evaluate how well connected the cell is to its neighbors, but also how its neighbors are connected to their neighbors and so on. You can see from the image, some of the biggest fluctuations in eigencentrality happen around the window and the columns. So we process the map again. And this time, we focus in finding the cells with the highest variances in connectedness. You can see a group of cells showed up, this time surrounding the features where we think the opportunities are, the opportunities for fleeing or hiding. We call those points of interest. In theory, the prey could use those points of interest as a shortcut to detect opportunities around the column and the windows. Instead of expanding the tree in every step in every possible direction, we can make the prey expand the tree only when it gets to one of the points of interest and only in the direction of other points of interest that are visible from that cell. We think this can facilitate all the hiding and fleeing strategies to show up because we cannot force the planning to move in the directions of the features where we think the opportunities exist. Something else is it will prune the tree by cutting many of the useless behaviors and letting the prey focus on the specific actions that really affect the reward function. So the next step was obviously modify our previous experiment and introduce points of interest to our simulation and just repeat it. And we started with a smaller number this time. So we started only with 1,000 predictions that we let the prey visit before making a decision. And the results were astounding. With this minimal sample from the tree, the survival rate climbed to 3.4%. Remember, at 100K, 100,000, we used to have 0.01%. So it was very small. And he was
Hey,
able to,
Herman,
yes.
I could you take one more minute, please, so that
Oh yes, I will wrap it up in 1 minute. And he was able, and also he was able to discover strategies using objects in the space to hide itself and make it to the goal. Let's move to the final slide. So we compared the results between these two methods, and we were able to reduce 99.99% of the sample of the tree that is necessary to create a good plan and maintaining similar outputs. This is still work in progress, but we believe we can enable with this technology an implementation for a fully independent robot with planning abilities that could successfully interact with an animal in real time. If you're interested in our work, you can play a game that we created in our lab that illustrates some of these concepts. That is in the URL that is there. And this is all. Thank you so much for your time. And I'm sorry we had this mishap at the beginning.
no worries at all. I'm going to, since we don't have any Q&A right now, I'm going to encourage the viewers to put questions in the Q&A, but I have a quick question for you.
Yes.
So, you know, your work is really interesting and, you know, so generalizable on beliefs about the environment. But then how animals also have like internal like uncertainties and beliefs. How do you think that would play with like uncertainties about the environment?
That is a great question. Yes. So the way that we compensate for uncertainty is by having to create more simulations. I'm talking from the computational biology perspective, right? So like we don't know exactly how that happens in biology. But the way that we compensate for uncertainty is by creating more simulations, for creating more possible values for the variables that we're interested in. So the only way to drive it down is by being more certain about the values or by knowing what are the possible values of those variables that we are not interested in or they will not affect the results. And I think that's where this research has some contribution on.
That's great. Thank you so much. So I'll applaud on behalf.